Refraction of light.
Let us do a small and interesting experiment to observe one of the light properties. Take a small, shallow bowl. Place the coin in the center of the bowl. While looking at the coin, lift the bowl up so that the coin can just no longer be seen in the bowl. Slowly pour water into the bowl while your eyes remain in the same position. Obviously, at first, the coin is hidden from your sight behind the rim of the bowl. As water is poured in, more and more of the coin becomes visible until the whole coin can be seen almost as if it is floating upwards. Amazing, isn't it? This is all because of refraction of the light.
The phenomenon of bending of a ray of light when it passes from one medium into another is called refraction of light. Let us now consider a ray of light traveling from medium 1 to medium 2, say from air to glass. The ray of light which approaches the medium 2 from medium 1 is called the incident ray. The ray of light will undergo bending in the same medium and is called the refracted ray. The angle between the incident ray and the normal is called the angle of incidence or the incident angle. The angle between the refracted ray and the normal is called the angle of refraction or the refracted angle. First law. The incident ray, refracted ray, and the normal to the surface at the point of interface all lie in the same plane. Second law, or Snell's law. The ratio of the sine of angle of incidence to the sine of the angle of refraction for the given pair of media and for the given color of light is a constant. Thus, sine I by sine R equals mu, a constant, and is called the refractive index of the second medium with respect to the first medium. For the normal incidence, angle of incidence I equals 0 and angle of refraction R equals 0. Snell's law is not valid. The refractive index is ratio of speed of light in the first medium to that in the second medium. Medium 1 mu medium 2 equals speed of light in medium 1 by speed of light in medium 2. Hence, the refractive index of glass with respect to air is air mu glass equals speed of light in air by speed of light in glass. The refractive index of any medium with respect to air or vacuum is called absolute refractive index. Here are some examples. Diamond 2.41, carbon disulfide 1.63, glass 1.5, ethyl alcohol 1.36, water 1.33. We will take an experimental setup of a sheet of glass and a torch. As the angle of incidence changes, the angle of refraction also changes accordingly. When we change the second medium from glass to water, refraction reduces. This is because water is less denser compared to glass. The angle of refraction depends on the density of the medium. As you have seen, different colors of light have different angles of refraction. This means that angle of refraction also depends on the frequency or wavelength of light. The higher frequency violet light travels slower and hence bends more than the lower frequency red light. This can be explained as visible light or white light is a small portion of the electromagnetic wave, having a frequency range from 430 trillion Hz violet to 750 trillion Hz red. From this demonstration, we have learned that angle of refraction changes when the angle of incidence varies for the same color of light and the same pair of media. Angle of refraction for a given color of light changes when the medium is changed. Angle of refraction is dependent on the color of light. Now we will look at some of the effects and real-life applications of the phenomenon of refraction. You may have seen sparkling diamonds in rings and pendants. Have you ever wondered why they sparkle? Diamonds sparkle because of the phenomenon of total internal reflection. Now we will learn about total internal reflection and its applications. When a ray of light traveling from a denser medium to a rarer medium, if the angle of incidence is greater than the critical angle, then it will not get refracted but totally reflected back to the same medium. This is called total internal reflection. Conditions for total internal reflection. 1. The ray of light must travel from the denser medium to the rarer medium. 2. The angle of incidence must be greater than the critical angle for that pair of media. Let's arrange an experimental setup of a glass tank with water and a torch at the bottom of the tank. Light the torch in such a way that a beam of light passes through the water and moves to the air above. We see that the light gets refracted. Now start changing the angle of the torch. When we reach the critical angle, the angle of refraction becomes 90 degrees. Now we will increase the angle on the torch beam again. Now the light would be completely reflected back into the water. What happens here is that as we go on increasing the angle of incidence, at one point it will become greater than the critical angle. This condition leads to total internal reflection. From this demonstration, we've understood that when light passes from a denser medium to a rarer medium and the angle of incidence becomes greater than the critical angle, total internal reflection happens. Now let's look at some of the applications of total internal reflection. The optical illusion of mirage that occurs in deserts on hot days is due to total internal reflection. The brilliance of diamonds is also caused by total internal reflection. The principle of total internal reflection is used in optical fibers for propagation of light. You have now understood the phenomena of refraction of light, total internal reflection, and their applications. Can you now list some other real-life applications of refraction?